To understand the freeze bias option, you need to understand how the P and the I portion of the PID algorithm works. I'm using the same little oven demo we've been using in the previous videos, and the system's holding steady at 110 degrees using a PID coefficient set from a previous video. The freeze bias option is currently disabled, and I've also enabled bumpless mode 2 so the set point doesn't change when we enter auto mode. Let's get a baseline with a P-only tuning. I'm going to switch to manual mode to reset everything and force the control output to 38%. We know from our previous videos that P needs to be around 24, and I'll disable the I term by setting it to a large number and disable the D term by setting it to 0. Let's switch to auto mode. Now remember, everything PID does is relative to when we switch to auto mode. In particular, remember that the control output was 38% when auto mode started. Let's bump the set point up 10 degrees to 120. I'll fast forward, and we see it only took about 2.5 minutes to get up to temperature, and at this P-only tuning, doesn't look bad at all, does it? This little oven demo system that we're using is responsive enough to give us a decent tuning with P-only. Let's zoom all the way into our 1-second sample time so we can see how it worked. Now understand, these 1-second updates are just when the display was updated. They're not the actual samples that were used in the PID calculations. But for argument's sake, let's pretend they are the actual samples. The CLICK PID equation looks like this. We've zeroed out I and D, so we just need to take the error, multiply it by P, and add it to the original control output, which we had set to 38%. So at this sample time, the set point rose to 120 degrees, which gave us a 10-degree error, which happens to be 10% of our process variable's range, which we had measured in a previous video to be 68 to 168 degrees. Put that into the equation, and PID sees that it needs to modify the original control output by 240%. Well, the control output only goes to 100%, of course, so it slams into this rail at the next sample time. If we scroll until the error is only 5%, PID still has to modify the control output by over 100%, so the control output is still maxed out. Looks like when we get to about 2.5 degrees, the control output starts to drop. Why? Because when we put 2.5 degrees, which happens to be 2.5% of the process variable range, into the equation, we see the control output drops to 98%, exactly what we see on the trend view. And that keeps going until the process variable gets close to the set point. But there's a problem. On paper, this all works perfectly, and the process variable settles out exactly at the set point. In many real-world systems, though, P-only tunings never come close to the set point because the error gets too small to affect change in the system. This little oven demo does respond to small changes, so it was able to get the process variable close to the set point. But if we zoom in, we do see there's still a small offset between the set point and the average process variable. Regardless of how big that offset is, the purpose of the I term in the PID equation is to close that gap by adding a bias to the control output to remove that offset. Now, I don't know about you, but this equation in the help file doesn't do anything for me when written like this. But if we realize that all this I term says is take the sample time times the first error, plus a second error, plus a third error, etc., and then distribute the sample time, so now we have the sample time times the first error, plus the sample time times the second error, and so on, and divide and multiply that by the I and the P coefficients to scale everything, then it becomes very visual. To see what I mean by that, let's run a PI example. The system's back to 110 degrees. Let's switch to manual mode to reset the PID algorithm, and let's set the control output to 38% again. This time, let's enter the PI coefficient set we got from a previous video, and switch back to auto. And I'll bump the set point to 120 degrees again. Fast forward through a few minutes, and zoom in on a steady state, and look at that. The I term has eliminated the offset. It took a while to get there, but the average process variable is right at the set point. Well, that's great. But if we zoom back out, we see we now have a new problem. This I term created this huge overshoot. And if we look at the P-only step and the PI step side by side, We see the PI step took twice as long for the process variable to settle out. So we sacrificed our performance to get a little better steady state. What happened? Well, remember our rewritten equation. It says take the sample time times each error and sum them. If we zoom in, so this is roughly one sample time, then graphically, that equation says take one sample time times the error. In other words, take this area and multiply that by the I and the P terms to scale it, and add that to the control output. Then at the next sample time, add in this area. Next sample time, add in this area, and so on. So the I term is simply calculating this area between the set point and the process variable curves. Over here, the error is negative, so this area gets subtracted from the control output. And eventually, things all settle out so the process variable is right at the set point. So the problem is, when we change the set point, we get a big error, which gives us a big area between the curves, so the I term gets large very quickly, so it'll take a long time for the smaller areas downstream to cancel that out. This trace on the PID monitor is what we call the bias. It's the original control output plus the I term of the equation. You can see on our plot that the bias grew way past 100%, and that alone was keeping the control output saturated. But if the I term is really only intended to remove the small steady-state offset out here, why don't we just tell it not to calculate the bias when the error is big? Well, guess what? That's exactly what the bias freeze does. It stops or freezes the bias calculations anytime the control output hits its min or max value. Okay, let's enable the freeze bias function and repeat the exact same step. Fast forward, and we got a much better response. This is P only, this is PI without bias freeze, and this is PI with bias freeze. Why did we get a better response? Well, when the control output went to 100%, the bias term was frozen at its last value. Look how flat the bias term is while the control output is at 100%. Once the control output came down out of the clouds, the bias started adding up all those little areas again, but since it started adding here, there aren't any large areas to add up, so the bias doesn't get all wound up and out of control. Which is why you'll hear some folks call the freeze bias option anti-windup. By the way, this is also why getting your sample time right is important. If you have a sample time that's real long, then you get a crude approximation of the area. If you have a really short sample time, then you get a super accurate estimate of the area, but you just unnecessarily wasted a bunch of processor time. So you want a sample time that's good enough. You can see why the I terms units are in seconds. It has to cancel the sample time, which is also in seconds. Some PLCs will have I in inverse seconds. That just means they're multiplying the sum by I instead of dividing by I. You can also see why a large value for I disables the I term. Dividing by a large number here makes this whole term insignificant. Well, hopefully that gives you a better feel for how this PID stuff works and why you almost always want freeze bias enabled. Click here to see all the videos in this series. Click here to learn about Automation Direct's free support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos.